So today, we're going to continue picking up where we had, or pick up where we had left off. So we had talked last time about functions, and then we had talked about domains and ranges. And today we're going to start by talking about continuity. So we say the function is continuous if there's no breaks in the function. Or another way of kind of thinking about it practically is if you can draw the graph for the function without having to pick up your pencil, that function would be continuous. What I want to really talk about mostly, though, is discontinuities. So there's three types of discontinuity. Two of which you've seen before. So the first type of discontinuity we'll talk about is the infinite discontinuity. And I'm just going to kind of use a picture or an example in a picture to kind of describe what we mean by this. So let's say we have a simple rational function that looks like 2 over x plus 1 minus 2. Hopefully you remember from last year that basically what the graph of this is going to look like. You'll have a vertical asymptote at -1, a horizontal asymptote at -2, and then you'll have two arms of your graph, one that looks like this, and then that one that kind of looks like this. And I'm not so worried about the specific points that go on those two arms. This is just kind of an exercise to talk about an infinite discontinuity. But you guys hopefully remember seeing things that looked like this last year, right? It's not an unfamiliar thing to run into. So this vertical asymptote here is an example of an infinite discontinuity. We say that because it's a break in the graph. I can't draw both arms of the graph without having to pick up my pencil, right? To go from this part of the graph to the next part, I have to definitely pick up my pencil. I can't keep drawing a line to get to it. And if I look at what the graph is doing at that discontinuity, one end is shooting down towards negative infinity, and one end is shooting up towards positive infinity. That's why we call it an infinite discontinuity. If both ends of the graph at the discontinuity are going either to positive or negative infinity or one end each. Is everybody okay with that idea? And you can have lots of infinite discontinuities in the same graph, right? And you guys saw that last year when you dealt with rational functions. You could have 2 or 3, or probably never saw anything with more than 3 vertical asymptotes in it. But you realize that you could. It just would be kind of tedious to deal with, right? Okay. The next one is called a removable discontinuity. So let's say that we have a rational function that looks like this. One of the things that we can often do with a rational function is they many times can be reduced, especially when the degree of the numerator and the degree of the denominator, one of them is greater than 1. So let's check to see if we can do any reducing here. So if I want to reduce this, I have to make sure I factor. So when I factor the numerator, and the denominator is already linear, so there's really no factoring to do there. we notice that the x plus 2 is in common to both. So we can reduce that, right? Does that all look okay to you guys? Now, what I've written here is not completely correct, though. Why is it not correct? Well, technically speaking, if I say that these two expressions are equal, then any value of x that I plug into one, I should get the same result when I plug that value of x into the other, right? That's what it means for two expressions to be equal. Well, what if I plug negative 2 in here? If I do that, I get 0 over 0. If I plug negative 2 in here, I get 1. So they're really technically not equal because there's at least one value of x that gives me a different result when I plug into each of them. Is everybody okay with that? Now, it turns out that negative 2 is the only value of x that causes them to disagree. So to update this expression to make it correct, we'll just say, okay, but you can't use negative 2. Now, why negative 2? Where did that come from? Yeah, it's the solution to the piece that I crossed out. Everybody's okay with that idea? You remember vaguely doing this last year, probably in your Algebra 3-4 class when you talked about rational functions. Fourth hour said they remembered this a little bit. Maybe they lied to me. I don't know. So if I go to graph this now, I can really just graph x plus 3. The only issue is, when I get to negative 2, there's like a little gap in my graph. Usually when we draw that, we just put like an open point there. It's like a point that you didn't fill in to represent that gap. And this right here would be your removable discontinuity. It's like there's a little piece of the graph that's missing. Is everybody okay with that idea? And again, trying to connect these to examples of things you've seen before, potentially seen before, I think is important, right? And I try to do that whenever I can, is connect this back to ideas that you saw last year. The third type of discontinuity, the one you haven't seen, is called a jump discontinuity. And our best example that we have for a jump discontinuity is when you're using something called a piecewise function. What a piecewise function is it's basically a function that behaves one way for one part of its domain, and then behaves another way for the other part of its domain. So if I was going to try to graph this, the first part of its domain, up until I get to 1, I'm going to graph as 2x plus 3. So it would look maybe like that. And then after that, I'm going to graph, starting at 1, negative 3x minus 1. So notice, because it's greater than 1 technically, this one is going to start with an open circle. Is everybody okay with that idea? So we call this a jump discontinuity because you're literally like going along and then you jump and start doing something else, something different. As opposed to the removable where you go along and there's just a gap and you continue doing kind of whatever you're doing before. So a removable is literally there's just like one point missing on your curve somewhere. A jump discontinuity is like to connect the two pieces, there's lots of points missing. There's like a segment missing. Is everybody okay with that? Okay. In terms of my expectation for you with continuity would be if you're able to identify the types of discontinuity in a picture. That's all I would expect you to be able to do with this. So if you had a picture of a graph, you could pick out which ones were which type of discontinuity. That's as much as I would expect you to be able to do. I don't even know that there's any homework that is based on this, that's based on this section. Okay? So it's, something where visual recognition is enough for me. All right. The next section, we're going to talk about increasing, decreasing, and constant. And this is something that at least fourth hour said they remember doing last year. Do you remember talking about functions increasing and decreasing and constant? Okay. So rather than going through and listing all the definitions, if we kind of remember this, I'm just going to kind of jump into some example just to make it a little less tedious of copying like definitions down that we already are aware of. Since again, we won't prove anything with this, so I don't need a, not having a precise definition, I think, is fine. So let's say we have something that looks like this. And we're just going to write down the intervals over which the function is increasing, decreasing, and constant. So when you're given a graph, that's not too bad, right? It's actually pretty easy. How many sections do you see that are increasing? One, right? And which section is that? Yeah, the part on the left that goes from negative infinity to negative 4. Perfect. And when we talk about increasing and decreasing and constant, basically what you're saying is that on this interval, if you pick one point and then you pick anything to the right of that point, if it's increasing, the slope between those 2 points should be positive, right? And you should be able to do that for any point to the right of it. That's why the endpoints are never included on these intervals, is because there is no point to the right that you can pick to find a slope between that. You know what I mean? So the endpoints on these intervals are always parentheses and never brackets. Okay with that? Okay. What's the interval where it's constant? Negative 4 to 3. Very good. That middle section here, where the graph is not sloping up or sloping down. And then decreasing is 3 to positive infinity. Remember, you're describing the x-coordinate, not the y. So even though the arrow is pointing down and to the right, it's to the right part that we care about when we're writing the intervals, because we're always describing where the graph is increasing or decreasing. So the where is always an x-axis question, not a y-axis question. The range is the only thing that's involving the y-axis. all these other increasing or decreasing or constants, or if you talked about positive and negative parts of the function last year, all of those are x-axis questions. Okay, so if you have a graph that's fairly easy, right, you can just look at the picture. What happens if we instead are given an equation? What would you do with something like that? Yeah, let's just graph it and then look at the picture, right? Don't need to make this any harder than it needs to be. I'm going to actually use Graphmatica to do this because I'm going to dump the image onto OneNote so we can highlight things on the image or whatnot, and it just makes it a little easier to, at least for me as the teacher, to deal with, or to get it into OneNote. Yes, sir. Of course. But you're right on in thinking that, like, well, I have this equation, let me just graph it and I can deal with it then. That's what I would do as well. Again, if you have a picture, it's not too bad. So this is the picture that I get. Those of you following along on your graphing calculator, I just want to point out to you that if you have something like this and you want to make a fraction, you can get your calculator to format everything to look exactly like this. If you press alpha and the y equals button, that's a shortcut to the fraction menu. And the one that you'd most likely want to use is just the numerator over denominator one. So you can type it in exactly as it looks like on your sheet of paper, which I think makes life, quite a bit easier to deal with, because you don't have to muck around with the parentheses. If you didn't have a parenthesis around the whole numerator and a parenthesis around the whole denominator, you would not have gotten the picture that I have here, which is the advantage of using that shortcut to the fraction command, is you can just type it in exactly like it looks on your sheet of paper and there's no parentheses to forget. I don't know if you've seen that shortcut before, but it's a good one. Again, that was alpha and y equals, and you can do that really anywhere in the calculator when you have a chance to input things. It'll always open up that little fraction shortcut menu. Okay, anyways, how many sections of this graph appear to be increasing? I see two, right? I see this section here, and then I see this section here. Everybody agree with that? Then in both of those two sections, you're basically walking uphill if you're going from left to right. Okay. This gap in between them appears to be a vertical asymptote. Pretty easily I can see by looking at the denominator, the vertical asymptotes are going to be at -3 and +3. Everybody agree with that? So I'll just kind of sketch that in real quick. Okay, so for my increasing interval, it's going to be a compound interval because I have two sections that are increasing, right? So I'm going to definitely have something with a union in between it. Everybody's good there? The first interval would go from what to what? -infinity to -3. Good. And then -3 to 0, right? So everybody's okay there? Notice that -3 is not included in either one of those intervals because at -3 there's an asymptote, right? So there is no point there to be that you can use to make increasing or decreasing with. Okay, is there anything constant here? Nope. Right, there's no flat section. How about decreasing? I see two decreasing pieces, right? I see this one here, and I see this one here. Do you guys agree? Okay. And just like before, because there's two pieces that are decreasing, I'm going to have a union between two intervals. What's the first interval? 0 to 3. Good. And then the second interval would be 3 to positive infinity. Is everybody okay there? Good. So again, if you're given an equation, I would probably just translate it into a graph and use the graph. And you can use your graphing calculator to obtain that graph, or if you're doing things on the computer, if you want to use Graphmatica, you're free to use Graphmatica, no big deal. Either is fine with me. Okay? If you're doing things on your homework and you're referencing a graph that's like, that I can't see, if you take a moment and just sketch a picture, it doesn't have to be the best picture in the entire world. You don't have to include any points for something like this. If you just give me a quick sketch of what's on your calculator, or if you dump in the image from Graphmatica like I did here, either of those is fine, just as long as I can see what you're looking at. Is that okay? Okay. Right along with maximums, or with increasing and decreasing and constant, we like to talk about our extrema, which is just our generic term for maximums or minimums. Except that's not the correct verbiage. It's maxima or minima, I think is the plural for maximum or minimum. Do you remember what a maximum or minimum is? It's the y-coordinate for a point that's higher or lower, depending if you're talking about a max or a min, or the highest or lowest point on some interval, right? Now, does it mean it has to be on the entire domain? If it is the highest or lowest point on the entire domain, we call that the global maximum or minimum. Otherwise, it's a local maximum or minimum. So let's just look at a couple of pictures here to kind of get the handle on this. I could probably do something that's less ambiguous there. Let's do that. I meant for one of those humps to be taller than the other, and it probably wasn't really close enough for a messy picture to you guys to believe that. So if I look at this, how many maxima do we see? 2, right? I see one here, and I see one here. Everybody agree with that? The one on the left, is that local or global? Local. The one on the right, local or global? This is global, right? How many minima do we see? 1. It's just this point here. Is this local or global? This is local. Why is it only local? Because there are points that are lower than that point. And those can't count as global because what point are you describing? There's always some point lower than whatever the point you picked because the arrow is going down forever, right? So this graph has no global minimum on it. Is everybody okay here? Okay. Okay. Let's do one more, like the weirdest thing I can think of. So let's say we have Oops. Let's do that. So this is a strange one looking here, right? I did this intentionally because it's like a lot of things like how are you gonna count these things? Okay. So here's a tricky question. How many maxima do we see here? I see infinitely many. Where are the infinitely many at? This flat section are all local maxima, right? They're all the highest relative point. Everybody agree with that? So there's actually infinitely many local max there. This guy out here is a global max. Is there a local max involved for this piece? There's not. Why would there not be? Because that's an open point at the end. It's not included. There is no final point on the left end of that little piece there to be a maximum, right? Any point you pick on that end, you can find one to the left of it, right? So there is no point there to call the local maximum there. That's tricky, right? If that was filled in, well, this wouldn't be a function anymore, for one. But if it was filled in, that would be a local maximum. Is everybody okay there? Now this one is very difficult because there's a lot of ambiguous things that you have to really kind of think about the definition. So are there any minima on this? There are not, right? We know there's no global because we have arrows pointing down, but even this spot here, which we might think of as a local minimum, it's because it's an open point. We have the same issue that we had that we just talked about. So that doesn't represent a minimum either. So there is just those infinitely many local maxes on this flat section and the one global max on the singleton point, and there's no minima in this picture. Which is kind of sneaky, right? This is harder than anything I would ever expect you to be able to do on a quiz or a test, by the way. But I figure we just, for something that's not a difficult idea, let's see, what would something that's difficult kind of look like? The things you'd get would look much more like those first couple, or that first example. Do you remember how you can use your calculator to find precisely where these maxima and minima are at? Let's just do that real quick, even if you do. Remember, I saw some people shaking their head. So if you look at your graphing calculator, this was a poor, that's fine. So this one has a local max right here, correct? To find a local max or to find any maximum or minimum, we're going to press second and trace and use either the maximum or minimum command, depending on which one you're looking for. This one we have a local maximum, so we'll pick the maximum. And now the calculator is going to ask us 3 questions. It's going to ask us for a left bound, so I need to take my cursor, which I can see flashing right here. It's probably hard to see because it's a little thing. And just move that left of where I think the maximum is. So I'll just use my left arrow. Doesn't really matter where it's at as long as it's left of that maximum and there's not another maximum or something in between. But that's good. I'll press enter. Now the question says right bound. So I'll just move my cursor now to the right of where I think that maximum is. Anywhere to the right of it is fine. Press enter. And then it asks for a guess. Here's the thing about the guess. Doesn't really make it go any faster. So, well, practically make it go any faster. Like if you pick a good guess, the calculator will find the answer a little bit faster than if you have a bad guess. But the amount of time it takes to like press the button to move the cursor is going to be longer than the microseconds of compute cycle that the calculator is faster. So I would just press enter again wherever you were at for the right bound. It doesn't really speed anything up. So we get this response. So I have 2.8935 times, and then this e to the negative, or e negative 7. What does this e mean again? This capital letter E here? Yeah, that's times 10 to the negative, right? It's scientific notation. So this number here is 0.000000289 and change, which is basically just what? 0, right? Everybody's okay with that? Similar with the y, right? We have 10 times 10 to the negative 14th. That's basically just 0. So the way your calculator works, it's doing an approximation algorithm to find this maximum, and it depends on like what the resolution of graph your setting is at. But if you have something like this that's like times 10 to the negative, really, like some really, really small number that's close to 0, the calculator really just means 0. This is like an artifact of its programming. Is everybody okay with that idea? But you have to be careful there, right? You have to look all the way to the end and look for the e. It'd be very easy to write 2.89 comma negative 1.86 as an answer, and that's not really what we're looking for there. This is really 0, 0. Everybody's okay with that? Okay. Good. All right, last section for today we're going to talk about is symmetry. So there's 3 types of symmetry that we're going to talk about. There's more than 3 types, but there's symmetry with respect to the x-axis. So WRT is just my abbreviation for with respect to. It's actually a common mathematics phrase, and commonly in mathematics we'll abbreviate with respect to as WRT like that. You may not have seen that before, but I'll do it on occasion here, at least when I have that phrase together. So what do we mean by something that's symmetric with the x-axis? So basically what I mean is something that looks like this. Or if I take 1/2 of my graph and I reflect it across the x-axis, it just overlaps the other half of the graph. Is everybody okay with that idea? So graphically, that's what it would look like. Algebraically, what would we be saying? Well, if I take some point, say here, that's like an x comma f of x, right? Oops. Negative f of x. And if I track up here, then this would be x comma positive f of x, right? Everybody's okay with that idea? So what I can say then is that f of x should equal negative f of x. right? That if I have like 2 comma 4, this would be 2 comma negative 4. So if I take 4, that should be equal to the negative of negative 4, which is what we're saying. What's one important thing to note about all of these functions that are symmetric about the x-axis, though? Look at this graph. Does it look weird? It's not a function, right? If you're symmetric about the x-axis, you're never going to be a function, which makes this one of our least interesting symmetries because you can't be talking about a function. At least the way that we've currently defined a function. The next one, symmetry with respect to the y-axis. So again, same idea. If you take 1/2 of your graph and reflect it across the y-axis, it should land exactly on the other half of the graph. And then algebraically, this would be the point like x or negative x comma f of x. And this would be x comma f of x. Well, I should probably say this as that, right? Negative x comma f of negative x. Everybody's okay with that? That's, and because these 2 points are on the same horizontal line, I know that f of negative x must be the same as f of x. So that's our algebraic. Interpretation. Worth noting that with respect to an y-axis, we often call these functions even functions. So that's another vocabulary. And really, more often than not, we use even function rather than symmetric about the y-axis, mostly because it's a lot less words. The last one is 180-degree point symmetry with respect to the origin. I'm going to tell you right now that we call these guys odd functions because I don't ever want to say that phrase of words again because, boy, it's a mouthful. So what does this type of symmetry look like? Let's look at an example here graphically. So basically what we're going to do is we're going to take 1/2 of our graph, and then we're either going to reflect across the x-axis and then the y-axis, or you could do the other order and reflect across the y-axis and then the x-axis. It doesn't matter. For the sake of argument, let's do the x-axis first. That would give you something that looks like this. And then when you reflect that across the y-axis, you get exactly the other half of your graph. So this is like doing both reflections. Is everybody okay with that idea? The other way you could think about it is like if you like tied down this piece of the graph and then you pulled this 180 degrees, like you swung it around, it should lie on top of the other end of it. You can think about it that way as well. That way I think is less intuitive than doing two reflections, but it works also. And then algebraically, what we're saying here is that f of negative x should equal negative f of x. So like here, if this is x comma negative x comma negative f of negative x, and then this guy up here would be x comma f of x. So if I negate the x and the f of x, this point would be the same as negative x comma negative f of x, and that's where this relationship comes, right? So if I start up here with x comma f of x, if I negate the x and the f of x, it would be back down here on this point, right? So that tells me then that negative f of negative x and negative f of x would be the same. Or if we just drop the negatives out front, that f of x should equal f of negative x. Okay. So what am I going to ask you to do with these type of symmetries? I'm going to ask you to be able to prove whether functions are odd, even, or neither. So notice that I'm using the word prove here, so you're not going to be able to just like draw the graph and say, oh, look, it's even because it has this symmetry. So we're going to do this algebraically, okay, is what I'm going to want you guys to do. So my first function that we'll do this for as an example, f of x equals x to the fourth plus 1. So if we look at our algebraic definition for odd and even, that's the not even, that was the first one. There we go. Writing down the right definition is important, right? Both of them start with f of negative x. You see that? So that's what I'm going to start with my proof. I'm going to compute f of negative x and see if that gives me one of these two things. And if it doesn't, then it's neither. If it does, then it's the one that I found. So when I do f of something, basically I'm just going to be plugging negative x's in place of the x's. Everybody's okay with that? Now what's negative x to the fourth give me? Just x to the fourth, right? 4 negatives make a positive, which is exactly what f of x is. So I can conclude this is even, because I have shown that f of negative x is equal to f of x. And that's our definition for even. So that is the logic and reasoning okay there? So the next one, g of x equals 2x cubed plus 3x. Well, we're going to start with g of negative x. So everywhere there's an x, I'm going to replace it with a negative x. What's negative x to the third? Well, negative x to the third, right? And then times 2 gives me negative 2x to the third. And then 3 times negative x is negative 3x. And I notice there that I can factor off a negative. And this part is the same as g of x, right? So what I have is actually negative g of x. So this is odd. Are we okay with that idea? Okay. One more example. H of x is equal to 4x squared minus 3x plus 9. So we'll start the same way. H of negative x. So everywhere there's an x, I'll replace it with a negative x. So negative x squared is just positive x squared. Negative 3 times negative x is positive 3x. And then plus 9. I notice here that this is not the same as h of x. Everybody agree with that? So I know it's not even. Okay, well, what happens if I try to factor off a negative? Maybe it's equal to negative h of x. Well, this part in here is not h of x either, so it's not odd. So what do I conclude then? That it's neither. Is everybody okay with the reasoning on that? Yes. Well, I have to check to see if it's odd. So I need to look at negative f of x. So if I factor out a negative, I'm checking to see if the part left over is f of x, which it wasn't, right? The signs were wrong. I guess h of x in this problem. Does that make sense now? Elizabeth, sorry, I'm working on the names also. So, okay. All right. Last little question here to see if anybody's observant. Now, I can look at these polynomials and know whether they're going to be odd, even, or neither before I do anything. Does anybody see what's going on here? How you can check whether they're going to be odd, even, or neither before doing anything to prove it. So, in fact, you'll know when you start your proof which one you should get as your result. In the Kristen. Okay, but on C, the exponent is 2, but that one didn't work. But you're right, it does have to do with the exponents. Okay, how many x's total? We're getting also in the right direction. The word you're looking for, rather than exponent, what you need is the degree. You remember what a degree was from? So if I look at the individual terms here, this term is degree 4. What's the degree for an integer or just a constant? 0, right? Because you could write technically you could write 1 times x to the 0 after it, right? So What do you notice about the degrees here? They're 4 and 0. They're both even. If we look here, the degree is 3, and the degree here is 1. They're both odd. If we look down here, the degree is 2, 1, 0. They're not all the same, parity, odd or even. So this one's going to be an either. So right there you can now tell just by looking at the polynomial function whether it's going to be odd or even. Just by looking at the degrees of the terms. Now that's not a proof, keep in mind. You still have to do the algebraic thing that we've done here. But it tells you exactly what the result should be when you're doing your proof, which is a nice thing to know, right? Like, did I do that right or not? Did I get the right result? Because I know what the result should be now. Keep in mind, this doesn't work if the function is not polynomial, right? That rule I gave you is just for polynomial functions. Now, it does work if, say, you think of f of x is equal to, like, the sum of, like, two even functions. That'll be even. But it's not really easy to tell if something is going to be an even or odd function unless it's a monomial, because all it depends on there is the degree. But we'll talk about sine and cosine functions and tangent functions and stuff later on. Those things are odd and even functions also, and you can make a similar argument there. Anyway.